Today I'm going to talk about LeetCode question number 1584, min cost connect all points. So you're given an array points representing an integer coordinates of some points on a 2D plane, where points index I is equal to x and y coordinate. The cost of connecting two points, xi, yi, and xj, yj, is the Manhattan distance between them, which is basically this formula, where val denotes the absolute value of val. Return the minimum cost to make all points connected. All points are connected if there's exactly one simple path between any 2 points. Okay, so one simple path between any 2 points is basically asking us to find the minimum spanning tree. And a minimum spanning tree is we are able to create a tree, make a tree or connect all points using with the least total cost. Okay, and least total cost meaning so these points basically have weights between them, and the weight between them is this formula, the Manhattan distance. Okay, and we want to minimize the cost of adding these edges to connect all points or make a minimum spanning tree. Okay, so the algorithm to do this is Prim's algorithm. Okay, Prim's algorithm. And basically how it works is, so additionally we're going to create an adjacency list of all these points. Okay, an adjacency list meaning from 0 and along with this adjacency list we're going to store the weight it will take to get to that point, starting from this key here, which is 0 in this case. So for example, and the distance will be Manhattan distance here. I'm not going to calculate it right now, but for example 0 will be connected to 5 points here. So it's blank 1, and then the weight to get to 2, and then the weight to get to 3, etc. And then for 1, its adjacency list will look like 1 connected to 2, and then to 3, and so on, and we're going to do the rest similarly for the rest. Okay, and basically each point is connected to each other. So if we have like 3 points here, okay, they're all connected to each other. Now let's add a 4th point. They can all be directly connected to each other. Okay, and that's how we're going to represent this graph here, and they're all directly connected to each other, and they all have a weight associated with each other. So how Prim's algorithm is going to work is we're going to have a heap, okay, and a visited set. And how we're going to stop this algorithm is when the length of visited is equal to the number of points on this graph here. Okay, so so basically like 5. Okay, because 1, 2, 3, 4, 5 points. Okay, so we'll stop when visited is the length 5, because that's how we know when we visited all points and connected to them. So with this heap, what we're going to do is start off at point 0, okay, and 0, 0, okay, and the weight to get to 0 is 0. So then what we're going to do is now, for all of 0's children, we're going to, and then our first iteration, of a Prim's algorithm, we're going to pop 0, okay, pop it, and then for all its children, and not only going to pop it, we're going to add this Manhattan distance to our total. Okay. Okay, then we pop 0, add its Manhattan distance to the total, and then we add all its children. Okay, 1, 2, 3, and so on. Okay, great. So now our next iteration of Prim's algorithm from our min heap here. This is going to be a min heap. What we're going to do is now pop the smallest element here. So for example, this was like 6, and then 1, and then 2. We're going to pop this guy here. Okay, so basically, to get from 0 to 2 is cost 1, and then we add that to our total here, so total would be 1. Okay, so then we have 2 as our target, as our point in focus. So now we add all of 2's children to the heap. And I'm just making up these Manhattan distances as we go along the way. Okay, so we then add all of 2's children to the heap. So it could be, I don't know, oops. We add the node 4, we add the node 5, we add the node 1, 2, 3. Okay, these are the points. Okay, so and I forgot to update visited, so we visited 0. Okay, and then we visited 2. Okay, now what are we going to visit? So a smaller one would be this one. So we will visit this. This has the smallest weight. Okay, we don't visit this 3. Okay, it doesn't have a smaller weight. So we visit this 3. Okay, so now minimum span tree to get from 0 to 2 to 3 would be 0 to 2 would be 1 plus 1 here, so total equals 2 right now. Okay, and then we pop 3 and add all of its children. We can have repeat children in here, but it's okay because we're only popping the minimum every time. Add 3 here, okay, etc. And that's how Prim's algorithm is going to work. The runtime of this is, so we're going to be popping from the heap basically n times, so log n, okay, and it's going to be actually n squared log n squared, because we're potentially visiting each of these nodes at least twice here. So like we're going to be visiting these nodes at least twice, popping them multiple times to our pushing multiple times to our heap here. Okay, so Prim's algorithm, runtime complexity is O of n log n. Okay, now to code it up. So first off, I'm gonna initialize my total number of points here, and just need the length of points. Okay, just to make my life easier. So now what I'm going to do is create my head adjacency graph. Okay, adjacency graph, and for I in orange, length of points, I'm gonna add it to adjacency graph initially as an empty list. Okay, so basically I'm gonna represent all these points as a number. I'll label them with a number 0, 1, 2, 3, 4, etc. Okay, and now I'll actually populate here, the potential neighbors of each point. So for I and range length of points, and also I'm going to label this as length I is going to equal to length I, okay, and then for j in range length during range I plus 1 all the way to length of points. Or I could use actually total points up here. Okay, what I'm going to do now is compute the Manhattan distance. So we'll call MD is going to be equal to, first I gotta initialize point j is going to be equal to points at index j. Okay, now the Manhattan distance is going to be equal to absolute distance of xi minus xj. So point I0 minus point j0 plus yi minus yj absolute value. Okay, so that's the Manhattan distance there. So now what I'm going to do is add it to the adjacency graph. So adjacency graph at I here is going to be equal to, or actually dot end Manhattan distance, and then the opposite way, since this is bidirectional, so 0 can connect to 1, 1 connect to 0. I'm going to do adjacency graph dot rj dot end md. Oh, and not just the Manhattan distance, I want to also record which node we're going to with this Manhattan distance. Okay, so from point I in the graph, the weight it'll take to get to point J is this Manhattan distance, and from point J in the graph, the weight it'll take to get to I will be this Manhattan distance. Okay, so basically we're done setting up our adjacency list there. So now what I'm going to do is have a visited set, and then a heap, and a heapify that. And initially we're only going to have one element in the heap. Push heap, and what I'm going to push here is 0, 0. Okay. Also want to keep a result. We're going to continually add the weights or Manhattan distances to this result. Okay, now onto Prim's algorithm. So while the length of visited is not equal to total points, what I'm going to do is pop from this heap. So Manhattan distance and point is going to be equal to the q dot keep hop keep. Okay. And if point in visited, we don't want to continually visit again and visit all these children again. Then we're gonna skip that. Okay. And otherwise, we're gonna add this node to visited, or this point to visited. So visited.add point. Okay. And then get all of points children. Great. Now for child in children here, what we're gonna do is, so if child 1, remember in here we're storing this tuple where Manhattan distance and then node. So at the first position, first index, we're going to be accessing the node. So if that is not in visited, what we're going to do is q.keep push and heap, and what I'm going to do is push the tuple child 0, child 1, okay, the Manhattan distance and the point. Okay, and one thing I forgot to do is add to our results. So okay, and finally, after all of that, we should be able to return result. Okay, I'll do a dry run. I'll use more test cases now. Great, and I'll submit. Alright, great, thanks for watching.